memory of what we're talking about. Now, what we're going to do now is talk about a variety of methods available to us for finding the solution to a system of equations. So I'm going to go ahead and make a list. Maybe you want to put the list right here on this page because you have a lot of space there. Let's list out all the ways that we could come up with a solution to a system of equations. So these are your methods for finding the special coordinate. Special meaning, what makes the coordinate special? True. Yeah, it makes all the equations true, and it's the point of intersection. So that's our special coordinate that we're interested in. So methods, there are 6. The first method is you can graph them. Because we have eyeballs, we can see, we can just graph all the equations and then look and see the points of intersection. Desmos does that very well. It finds the point right there. 2, there's something called systematic guessing. So ultimately you're guessing, but it's not just pure blind guessing. There's a method to it. Now there's 2 old techniques that you might recall from high school. One is called substitution, where you substitute one equation into the other equation, and that allows you to solve for a variable. And then another method is called elimination, which is where you add 2 equations together and it eliminates one of the variables. The next 2 you might not have ever seen before. The first one is called matrix inverses. And you can use the inverse of a matrix to solve a system. And the last one is called matrix determinants. And you can use the determinant of a matrix to solve a system as well. Okay, that's just a list at this point, right? We've seen how to do the first one. We just graph it to find the point of intersection. Systematic guessing, we'll try a couple of those, and then we're going to review substitution and elimination. And this will probably take us today and the next time. And then we'll do matrix methods when we're done with those. All right. So again, what are we trying to do? What are we trying to do? Yeah, we're trying to just find the points of intersection. Which, how do we know that we found the correct point of intersection? You plug it in and it makes both equations true. Okay? So that's what we're trying to do. All right. So the first method, which we've already done one of, well, let's go ahead and try it one more time. Let's solve these by graphing. And we'll do the whole thing. We'll graph it, we'll find the point, and then we'll check to see if the point's really true. Now, we already did a question just like number 4. So let's do number 5. How do I graph this? And again, remember, it's always helpful to remind yourself formulas just by writing down y equals mx plus b and m equals the up, down, over the right, left. It gives you something visual to look at rather than just trying to remember all this stuff from the dark recesses of your mind. Write it down and then you can look. So, what's that? That's all you have is the dark recesses of your mind? Yes. That's right. So, for the first equation, what's the slope? Yeah, it's an invisible 1, which is really 1 over 1 because it has to be a fraction. So our y-intercept is -4, and then our slope is up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1, or down 1, left 1, and that's our first one. The second equation, what's that slope? It's a -1, which is really -1 over 1. Okay, so take a moment and start making your graph. Very comfortable. Okay.
Down 1.
Yeah, down 1. Yeah, down 1, right 1, down 1, right 1. So the next one, you start at -2, and you'd say down 1, right 1, down 1, right 1, or the opposite of that, up 1, left 1, up 1, left 1. So now we have these 2 lines. And again, the point of intersection is visually clear. It should just pop right out at you. There's my point of intersection, and that's 1, 3. Now, that's just convenience. Since we have eyeballs, we're not done yet. We now need to actually plug that coordinate into both equations and see if both equations are simultaneously true. So we have y equals x minus 4. I'll check that equation first. And again, it's helpful to label. This is x, this is y. Because typically when you're plugging the numbers in, they go in backwards. Y actually goes first, so that's -3. X is 1 minus 4. And sure enough, -3 equals -3. So that one's true. So now we need to check the second equation, which is y equals -x minus 2. So again, we plug in -3 for y, and then -1 minus 2. And that's -3 equals -3. So that's also true. So now we know for sure that we have the right answer. So what?
So we're just like our answer is basically us what we do when we check.
Yes, correct. This is how you really, really, really know that this is the correct solution. Because after all, if you just graph two lines and then see where they intersect, do you know for sure that you graphed it correctly? You could have made a mistake. You could have graphed the wrong slope. You could have started at the wrong y-intercept. Every once in a while, I see people start at x-intercepts instead of y-intercepts. There's a lot of mistakes you can make when you make a graph. So just graphing and seeing a point of intersection is not enough. So yes, thank you, Hector. You have to take that point and actually plug it into both equations. And what you want to see is both equations becoming true. Yeah. But in fact, Hector, I mean, kind of like, if you were just, Hector. Yeah, if you were just
writing it down.
Yeah, I mean, if you just could produce a coordinate from thin air, but then you showed me that it made both equations true, I'd be like, no, that's the answer. You know, regardless of what method you use. And that's kind of the point. There are 6 different methods for producing the coordinate. But in all 6 methods, you still have to just take that coordinate and plug it into both equations and see if both of them are true. I don't know what that is. Is that okay? Oh, well, that's fine. All right. So that's called the graphing method. We don't have to do any more of those together. So let's just go ahead and turn the page. So that's method number 1, graphing. If you have graph paper, you can do it by hand. If you have your TI-82 handy, you can just graph it on there. You can do it on Desmos. A lot of graphing methods available to you. Now this next question, at first just might seem like a brain teaser or a riddle. You know, some sort of game you might play with friends at a wild party. Yeah. So it says here, a farmhouse shelters 9 animals. And how many animals are in the farm?
9.
9. Sí, correcto. Some are oxen and some are geese. What's an oxen?
Ox.
It's an ox, like a big cow, right? There's some horns on it. And then what's a geese? Or a goose? Cow. Oxen and geese in the same farm sounds like a bad idea, but they're all in the same farm. Now, altogether, there are 22 legs. Basically, like you went out and counted, you're like, hey, okay, how many oxen legs, how many legs does an oxen have? Or how many legs does a goose have? 2. So somebody went out there and just counted legs. And then they came back and they're like, I have a riddle for you. There's 9 animals of oxen and geese. There are 22 legs. How many of each animal are there? Okay? So I'd like you to go ahead and just solve it on your own using whatever method you can. It's a riddle. Okay? You're at a party. You're trying to win the game. So just, forget the fact that you're in a math class, forget the fact that you know algebra, forget the fact that we're talking about systems, and I want you to tell me how many oxen there are and how many geese there are. You can draw pictures of oxen and geese if you like. You can do any method at all. Just solve that riddle. You did? Fun. There's only one answer. I mean, that's an interesting question. Is there more than one answer? All right. Who thinks they have the solution? Okay, go ahead.
Since some off and some east. So, and our number of panels unit at 9.
Yeah.
So all in all, because it says some oxygen piece, there are at least two oxygen pieces.
Oh, because of the word some.
Yes.
Okay. Now, Tiger raises an interesting point that the use of language can sometimes have certain implications in which we assume certain things, and maybe as assumptions are okay, maybe not. And some, I think, I don't know if the technical definition is, but it allows for the possibility of zero. And maybe if you use the word couple. Unfortunately, it's terrible. English is not necessarily the best for that. When they say some, they're just saying that there could be options, there could be keys. That would be a better use of language. But Hector, that's a really good point out. Sometimes language could be really misleading. But I do like what you're saying a lot, Hector, is that you know that you have oxen and you have keys, and all together they should add up to 9. And so you were saying that the number should be 2 or more, maybe. But really, what could they be? Like, what are my possibilities for oxen and keys? I could have 9, or I'm going to start at the smaller number. There could be no oxen, and all 9 of them are keys. There could be just 1 oxen and 8, or 2 and 7, or 3 and 6, or 4 and 5, or 5 and 4, or 6 and 3, or 7 and 2, or 8 and 1, or 0 or 9. Right? So let's do it. Yeah. So Hector, you were suggesting that you might only have to look at those numbers, right? But really, we're saying, okay, we got to look at them all. Okay, so good thoughts so far. What else? What were your kind of thoughts on how to go about finding the answer?
So I just draw 9 animals with
Yeah.
no legs.
You drew 9 animals with no legs.
Yeah.
That's brilliant. Seriously, I love it. That's great. I've never thought of that before. Wait, you're serious? So you drew 9 bodies. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then what did you do? You just
then
did
I started
2.
with 2 legs each.
So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18.
And then 2 more legs.
19, 20.
And then 2
Or 122. That is one of the most fun solutions I've ever seen to this problem. And it's because I'm so lame. Like, I am so destitute of imagination that I never thought to solve it that way. That's super fun. I like it. Okay, you got the solution. What's another way? Gabe, how'd you do it?
I kind of like a sandwich.
Tell me.
So I started with putting oxen equals 4 legs, geese equals 2 legs, and then I started at 3 oxen, and I got 12, and then I got 6 geese. I equal 12, it was 24, so I just went that one.
Oh, okay, very, very nice. Yeah, I like that. I don't know how to write that other than how you wrote it. But you basically started with, okay, so watch, folks.
It was like a guess.
Yeah, it was a guess. So so for oxen and geese, what Gabe did was say, let's just say that there's 3 oxen and 6 geese. Like, that was just a first starting point guess. And he knew that this would be multiplied by 4, this would be multiplied by 2. So that would give him 12 plus 12, which is 24. But that's too many legs. And if you want to get rid of legs, the only way to get rid of legs is to get rid of oxen. So he converted 1 oxen into a goose. So then he had 2 and 7. And then he just tried again. He said, well, okay, now I have this. And then that's 8 plus 14, which is 22. And he got his answer. Yeah. That was fun. Is that what?
Oh, that was smart.
Okay, that makes sense? Yeah. This is the kind of solution I often do. Yeah. Nadine, what'd you do? Okay, that's okay. That's okay. Brain teasers are tough sometimes. Okay, so let's go back to this table that I have up here, because this is what I'm going to call systematic guessing. So notice the way that Gabe did it, he just kind of started somewhere. Right? He started at the 3. What inspired you to choose 3?
Well, I was just thinking about the oxen first. But I looked at 4 first. I didn't write it down. I looked at 4. It's too funny.
Okay.
Well, I was looking at number of animals total. 9. If I were to have 4 oxen, I would have enough.
Sure. Okay, I like that. Now let's take that into this table, okay? So we agree that this table has every possibility. And since the oxen is going to be multiplied times 4 and the geese is multiplied by 2, I could go ahead and look at the 2 extremes. Right? So this extreme, 9 times 4 is 36. 36 legs is way too many. And way down here, 9 times 2 is 18. That's way too few. But where's 22 going to be? Closer to 18 or closer to 36? Closer to 18. And in fact, if I try one more now, 4 times 1, so 4 times 1 plus 2 times 8. That'd be 16 plus 4 is 20. And then try another one, so 4 times 2, 2 times 7. So that's 14 plus 8 is 22. Well, already that's my answer, just by working my way down the list. But also, we would notice after a while, what's the pattern here?
2.
And we're adding 2, which makes sense. Because every time you take away an oxen and put in a goose, what happens to the amount of legs? It's a difference of 2. Yeah, well, I guess in this case, I'm adding an oxen. So if I take away a goose and add an oxen, I'm adding 2 legs every time. Whereas if I think of it this way, if I take away an oxen and add a goose, I took away 4 legs and added in 2. So that's taking away 2 legs overall, and I would have done that 2. Okay, so there's a lot of structure here, right? Called the pigeonhole principle. And the pigeonhole principle would state something basically like that. That if you have 9 pigeonholes and 22 pigeons, and you want to shove pigeons into pigeonholes, you just start putting them in until, according to the structure you wanted, which was either 2s or 4s, and you did exactly that. I know that sounds really silly, but it's actually like a really important principle in mathematics. Okay. All right, so everybody go ahead and solve number 2. Look at your split. You have a lot of ideas now about how to solve it. You can choose any method you like. Go ahead and solve number 2. How would you solve this one? Oh, so what did you do? Yeah. So what did you do? A very so what is that idea here? So 1, 2, 3, 7. Building true. What if so what if you give them all 4 legs? 36 legs. And so then what you do is you start amputating legs. So you amputate 2, that brings you 34, 32, 30, 28, 26, 24, 22. And after that many amputations, you're down to the number of legs you need. Olivia, you just invented not the pigeonhole principle, the amputation principle.
Amputation.
Yeah, well, it was a little more harsh, but it's pretty interesting. You're like, what? Oh, that systematic approach? Hey, you like the systematic approach? That's awesome. Oh my gosh, super fun. Okay. And Hector, how are you going about solving it? Okay. See, Livia, I guess you started with 2 legs on everybody and you gave additional legs. That's like you did the prosthetic leg approach. Okay, so a lot of ways to go about it. Again, we could do the approach of if you wanted to do, so there's 13 animals, cows and ducks, so it could be, let's see, 0 and 13, 1 and 12, 2 and 11. And I'm just going to say, I'm going to start with cows having all of it. That's more legs than I need, and it ducks. And so then 4 times 13 is 52. That's way too many. But every time I shift down, I'm subtracting by 2. So that would be 50, 48. Oh, this is going to be a long time. Yeah, I'd have been better off the other way. Oh, geez. Yeah, that took way too long to get down there. So that'd be 1, 2, 3, 4, 5, 6, 7, 8. Oh, no, better yet, that's 13 cows. So 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3. So 3 cows. Is that what everybody got? Was 3 cows? Yeah. And then 10 ducks. Okay. Okay. I got it. Double check. Thank you, Hector. What do we do? How do we know if we have the right answer? We have to check to see if it fits the bill, right? So first of all, are there 13 animals? 10 and 3, so 13. Does yours add up to 13? Darn. Okay, so that's what happened. Okay, now let's convert this into an algebraic problem, okay? I'm going to introduce to you a very nice approach to solving word problems. It's 2 steps. We're going to turn this word problem into an algebra problem, okay? Step 1 is define your variables. So what variables should we use? We're going to define our variables. So first of all, how do you know which variables to use? You look at the question. The question, okay, there's a question mark there. The question mark is always going to tell you what your variables should be. So what's the question? How many of each animal are in the field? So the first thing we'd say is let x, hold on. You say let x equal the number of cows, and then let y equal the number of ducks. Right? So step 1, define your variables. This is a strategy you can use for any word problem. The first thing you always have to do is define your variables. And you find your variables by looking at the question at the end. Okay, now step 2, you create your equations. So we now need to go and create our equations. And keep in mind, we're talking about systems of equations. So how many equations do we expect to have? 2. So let's look at the information they give us. The first piece of information is that there are 13 animals. Right, yeah, so what would our first equation be? We have to use the variables x and y, and we need an equation that somehow equals 13. X plus y. Exactly, just x plus y equals 13. Cows plus ducks equals 13, right? So there's one equation. What would our other equation be? We have to go look at the other piece of information they give us. There are 32 legs. So we need an equation that says something, something, something equals 32. So what's that equation going to be?
Or do we have to go back and find a different variable, or could we just, so
It's gonna be this, it still has to be X is cows and Y is
so
ducks.
could X be number?
It cannot. We've already defined our variable X to represent the total number of cows that you have. So we need to stick with that definition of our original definition of the number of cows. Because again, that's what they're asking us to find. So we wouldn't want to let X equal something that they're not even interested in.
Would it be 4X?
Yeah, exactly right. Now keep in mind, folks, this first equation was about the total number of animals. What does 32 represent?
B.
Yeah, the total number of legs. And therefore, each component should tell you how many legs there are. So how many cow legs are there? 4x. Because for however many cows there are, you multiply by 4. And then how many duck legs are there? Yeah, 2y. Because for however many ducks you have, you multiply by 2, and that'll tell you how many duck legs.
I want to try this with sharks and whales.
Sure.
And like how many fins?
Okay, fins, yeah, not feet.
No.
It'd be just as funny if you're like, you have 20 sharks and whales and no legs. How many are there? You're like, well, there's no way to know. Okay, well, so that would be our system. What would we do from there? Well, the only approach we've come up with so far is graphing. And now that I have x plus y and 4x plus 2y, I easily rewrite the first one as y equals negative 1 over 1 x plus 13. And I can rewrite the second one as y equals negative 2 over 1 x plus 32. And then I can just graph that and find the point of intersection. And in fact, folks, take a look. What if I do go ahead and graph that? On Desmos, I'm going to graph y equals negative x plus 13. And then y equals negative 2x plus 32. I did something wrong.
I was going to say, the reason why you put the negatives is because you switched the order.
Oh, plus 16. Yeah, because I moved it over to the other side.
Okay.
There we go. Where's the point of intersection, folks? 3 and 10. Now, how do I know which is which? Yeah, because of x and y, right? So by graphing this equation, I got the solution 3, 10. And now I know that this is a coordinate x, y, therefore x is 3, therefore by my definition, x is the number of cows, there are 3 cows. And by my definition, y is the number of ducks, there are 10 ducks. So that kind of closes the loop. So how was that? Seeing how to turn a word problem into an equation. And then you can just graph it, right? We'll do that. We'll do some more of that. Okay. Now, that's our first 2 methods so far. All right, so we can graph something, and we can do systematic guessing. So the next kind of step we're doing is we're going to go to algebraic techniques. And algebraic techniques are nice for 2 reasons. Well, they're nice for lots of reasons. But first, you don't need graph paper, and you don't need technology, and there's no guessing involved. With substitution and elimination, if you follow the algebraic procedure, you will get the answer. So there's no guessing, you don't need to graph anything, it's just algebra, boom, 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 there's the answer. The last 2, you need to make a matrix, which we've never done matrices before in this class, and maybe it's been a while since we've ever done a matrix. So we actually get to use our calculator for this. This would be a calculator technique. In any case, let's take our break, and then we'll come back and we'll learn the algebra of substitution and elimination. So the time is 1:31. Let's be back at 1:40.
That was me.
I'm saying like, hey, you're wrong.
Me voy a poner eso. Así. No te tengo. Por eso te voy a esperar. Esperar. No, nos alegramos en Facebook. Cuando empecé a hablar, se trabó. That's me. Tú ya empezaste. Yo empecé, ¿no? I want to get back to my high school years. It was, I was junior. And I went to prom. Viendo esa foto todos los días. I'm gonna put it in. 2 years ago?
What happened?
When we were skinny. She was skinny 2 years ago. I was skinny 8 years ago. Yeah, I gained so much weight. Don't get a weight.
This is you?
That's her.
No, it's the makeup throws me off.
I was
Your hair looks nice. What's looks nice? It's not as.
no, well, I have a style. I'm so pretty. Dude, I was so now like I need to we have to go hiking. There's one this weekend. Really? Yeah. Oh, wait. You get it? La ceja de lo que te estás haciendo, la ceja. Stupid. Why do I do it? What do I do? You know what? Dude, we haven't really experienced it before this time. This was my mom. ¿Por qué lo haces? Yo lo tengo por ahí. Yo lo quiero vender por ahí.
All right. Thank you.
Yeah, I think you know this feeling. The feeling when you get a problem, you do a problem, you got it wrong, you again feel like you got it right, and feel like such an idiot the way you got it wrong.
Yeah.
Just by a simple sign change.
Oh yeah. I of course have that feeling. I struggled for half an hour before coming to this class just to get Excel to make a superscript. I couldn't make it happen. Even though I was following the correct steps and it even happened, but then I'd click somewhere else and it'd go away. Okay, where's Nadine and Gabe? Can't start with that.
And then it's like,
So you know Spanish,
Some-
some Spanish, so you understand. Like if I talk to you in Spanish, you te voy a hablar español.
Isn't that so sad?
The whole time I'm passing the car. You go real quick.
here, look at this.
Sad.
At least I have some.
Okay, folks. Here we go. I don't know where Nadine is.
I was blind for 4 hours.
Tiger? Valeria? Emily? All right, here we go. I think it's time. Yeah, totally time. All right, let's keep going. So we're going to start an algebraic method called substitution and elimination. We'll do substitution first. Substitution, just like the name implies, you're going to take one equation and substitute it into the other equation. It's a pretty exciting idea. It reminds me of that movie Inception with Leo DiCaprio.
Is it kind of what we're doing with the F and G?
Yeah, absolutely. You're substituting one into the other. Yes, for sure. That's exactly right. It looks a little different, but it's the same idea. Now, in order to even use the substitution method, what you need a substitution sentence. So we're going to use this phrase, a substitution sentence. This is going up there at the top, which is either y equals or x equals. So you need one equation solved for one variable. Okay, it doesn't matter which. You can solve for y and make one of the equations look like y equals, or you can solve for x and make one of the equations look like x equals. Your choice. So in number 2 then, do we already have a substitution sentence? Yeah, in fact, we have 2. So you can take your choice. Either one of those is going to work as a substitution sentence. Yeah, so just for fun, let's use the first one. Now watch how this happens. You choose your substitution sentence. I'm going to sentence. And I'm going to take what y equals, and I'm going to plug it in to the other equation's y. Okay, so the first equation is telling us what y is equal to. So then I go to the other equation, and wherever I see the letter y, I'm going to write this equation empty for the letter y. So it's going to be something equals negative 2x plus 6. And what do I put in where the y used to be? 3x minus 24. Then you solve. Now, a really interesting philosophical shift just happened here. See, what I have up here is two equations written in two variables. And there's a general principle in mathematics that you can only solve for as many variables as you have equations. So I have two variables, two equations. That means I should be able to solve for x and y. But see, if I just have y equals 3x minus 24 all by itself, that's two variables in only one equation. You would not be able to solve for a solution. You're just kind of stuck. What you need is two equations to solve two variables, three equations to solve three variables, four equations to solve four variables, and so on. And so right now, I started with two variables and two equations, but now look what I have. One equation and one variable. And that means now I can solve for x. So I absolutely can't solve for x now. So in general, with a linear equation, you just move your x terms to the left and your number terms to the right. So I'm going to move my x terms to the right. I'm sorry, x terms to the left. So 5x minus 24, 6. And then move my number terms to the right. So add 24. And so now 5x equals 30. And I divide off the 5. And I get x equals 6. So again, what we accomplished by doing substitution, by plugging one equation into the other equation, you would create one equation in one variable. That means you are able to solve for that variable. So we did our work, just basic algebra. Now we have x equals 6. Yeah.
For some reason, I would have figured that kind of like what we did with the to put 3x minus 24 into where the x is and then negative 2. Is that possible?
Well, you can do it. It just wouldn't give you any.
Right.
Yeah. Yeah. So what you're thinking about is function substitution, where you're not function substitution, function composition.
Oh, okay.
But what we're saying here is we're saying y, in fact, is equal to 3x minus 24. So right there where I see the letter y, instead of writing the letter y, I'm going to write 3x minus 24. Yeah. Yeah, and that's very important, Gabe, that you're substituting in for the right variable. Because if you did substitute in for that, just watch and see that it wouldn't have done anything at all. If I write down y equals negative 2x plus 6, and I go ahead and plug in 3x minus 24 right there, then I'd have y equals negative 6x plus 48 plus 6. And I still have one equation and two variables, which means I can't solve. Okay, so now, folks, are we done? X equals 6. What are we looking for? What are we looking? Yeah, we're looking for a coordinate, a point of intersection. We're looking for an x and a y. So far we've solved for x. We still need to solve for y. And now the beauty here is we want to solve for y, right? Well, if you have a substitution sentence in the form y equals, you already have an equation to tell you what y is. And so what we're going to do is take our x equals 6 and plug it right back into the original substitution sentence. So y equals 3 something minus 24. So we plug our 6 into that. And so then we have y equals 18 minus 24, which is y equals negative 6. I don't know why, but I feel like this reminds me of the Ouroboros. You know the Ouroboros?
Yeah, the snake who bites his own tail.
Yeah, the snake who bites his own tail. So what happened here? We started with a substitution sentence. We plugged it into the other equation. And then when we got out of it, we plugged back into the original. So to me, that kind of looks like the Ouroboros. I don't know how to even spell that. Is it Ouroboros? Anybody? That's a lot of O's and U's in there. I don't know if that's correct. But that's the Ouroboros, which I assume the snake is happy. I don't know. Probably not. It's probably like, oh gosh, why am I doing this? I don't know. All right. I don't know. Okay, now, again, what's the answer? It's not two different things. It's one thing. The answer is 6, negative 6. It's a coordinate. Now, are we done?
Just plug it back in.
Plug it back in. Yeah. Right now, we have to plug it back in because remember, there are two definitions. It's a visual point of intersection, or it's a coordinate that makes both equations true. The real thing we're looking for is a coordinate that makes both equations true. So you do have to verify that it makes both equations true. The good news is you can just do scratch work. Okay, this is up to you. I should be able to see some scratch work on your paper. But like right now, if I just go back to the original problem, I'm going to put a 6 right there where the x was. I'll put a -6 right there where the y was, and I'll just check, right? So 3 times 6 is 18. 18 minus 24 is -6. Boom. That first one's true. -2 times 6 is -12. -12 plus 6 is -6. Boom. That one's true. So that's as simple as you need to do it. You can just go back to the original equation. I should see some sort of chicken scratch up there that makes me think that you really did plug that coordinate back in and see that it was true. If you're not going to plug the coordinate in to make sure that it's true, why did you even do anything in the first place? Right? Okay, because that's the proof is you're finding a coordinate that makes both equations true. All of this is just methodology to produce a coordinate that then you plug in to see that it makes both things true. Well, we're interested in finding a coordinate that makes both things true. Okay. Okay, all that done. Everybody try one more all by yourself. So we need a substitution sentence. Might as well just choose the first one. So y equals that thing. That's your substance. And you're going to plug that into the other equation to y, and away you go. Lee, thanks again for helping with that 6 tradition. Of course. Now, did it work in your normal Excel program?
No.
What do you mean, no?
Like, when I was trying to do it, it wouldn't work with me. But that's how I figured out how to actually.
But you were on a PC with regular Excel. Yeah. And did it work?
No. When I was trying to do like the way you're doing it, it wouldn't work. So then that's why I was like figuring out what I could do. Figure out.
I know there's a lot of problems in animation and in the world. But the fact that Excel wouldn't subscript my number today.
I even tried sheets.
Yeah.
Sheets. They wouldn't do it on there.
That's really weird. I need someone to call. If Steve Jobs was still around, I'd call him. He's not around that.
Are you gonna call?
I need to call somebody about the fact that Excel is not subscripting. Yeah, very good. That's great. Yep. Like this. Not as I'm math related. Show me after this. Okay. That's there. Oh, you already did that one, and it worked. Oh, great. Let's go, Nick. Yeah, I really like how you're verifying all your answers in your calculator. That is a best practice. Do you know how many problems that I've gotten wrong lately in my own class because I messed up on the calculation? Oh, I'm using my calculator all the time. Oh, yeah. There's no good reason not to check answers on the calculator. So if you'd like to confirm your answer here, we're plugging the negative. So I'm going to write it empty. I know this is so obvious. You just set that thing equal that thing, but I'm plugging it into y, so negative 5x plus 19. So then I bring my x's to the left, which is negative 8x plus 19. And I bring my numbers to the right, which is negative 8x equals negative 32, and divide off the negative 8. And did we get x equals 4? If you got negative 4, go back and check your signs.
Always keep my x's positive.
No, I got positive.
We do.
Yeah.
Great. Okay, so now that we have 4, remember we're looking for a coordinate. So we need an x and a y. So now to find our y, we go back, plug it into our original substitution sentence. So negative 5 something plus 19. And then we're plugging it into 4. So then that's y equals negative 20 plus 19, which is negative 1. Now, you've all heard me say plug it back into the original substitution sentence. Is there a problem with just plugging it into the other one? Will the other one work? What happens if I plug it in the other one? So does it matter? No. I think philosophically, I like the idea of closing the loop more, the Ouroboros, right? So you're utilizing both equations. One gets used to plug into the other, and then this one is technically the equation solving for x. So then looping it back and plugging it back into the original substitution sentence, I think that's just nice. Plus, this one is not always going to already be solved for y, whereas the substitution sentence is guaranteed to already be solved for the variable you're interested in. So it makes more sense to go back to the original. Okay, so our coordinate is 4, -1. Is it correct?
Maybe.
Maybe.
Is what I would say if it wasn't right.
Yeah, well, that's the right answer, Hector. Maybe. But, you know, again, we've done really lots of good algebra up there, but we have no idea yet if we're right or not. So we plug it in. I'm going to put the -1. That's correct. 1 minus 13 is -1. That's correct. So, yeah, checking that your coordinate is correct is a simple matter of doing that work up here. You can also plug it into your calculator, whatever you want. All right, so folks, that method is called substitution. And what do you need in order to do substitution? You need a substitution sentence. You need something y equals or x equals. Doesn't matter which one you choose. So let's turn to the next page. And here's another example where only one of the equations is ready to go as a substitution sentence, right? So if you just need a substitution sentence, by all means, if they give you one, that's the one you should use. So here is my substitution sentence. And I'm going to plug that in for which variable? I'm going to plug it into x or y? Yeah, for y, because we're saying this is equal to y, so we're going to plug it into that y. So you see how I circled my substitution and I put a little arrow and I pointed it at the y? I think that's a nice, helpful best practice. Tells your brain and your audience what you're doing. So now, again, this other equation that is not my substitution sentence, I'm going to write empty. So I'm going to go ahead and write down 16x plus 2 empty equals 6. Because that now creates a space for me to do my substitution. So I'm going to plug in -8x minus 3. And again, you'll know that you plugged it in for the right variable if you result in one equation in one variable. There's slightly different algebra this time, because it's just a matter of distributing and then combining like terms. We have 16x minus 16x minus 6 equals 6. And oh, how interesting. The x's cancel out. And now we have -6 equals 6. Now just for fun, you can finish the algebra and move all your numbers to the right. So I'm going to move that 6 to the right. And we end up with 0 equals 12. Curious, is 0 equal to 12? No, it's not.
After it would be, yeah, it would be.
Yeah. Okay, so what does this mean? Now keep in mind, what we're doing now is we're going blind, right? We're not visual creatures right now. We don't have an XY graph. We can't just look at the graph and see where the point of intersection is. We're attempting to do all this algebraically. So we just did algebra, but the variables canceled out. So did we solve for x? No. Okay, so what that tells us is that we're not looking at this system right here. So what other type of system could we be looking at? Everybody look over here. It's not this one. So it could be parallel, or it could be overlapping. We don't know which yet. So let's look at the algebra, because it really does talk to us. It tells us what it is. We're looking at this, and first of all, I'm just going to be a little playful here. What we're doing when we do algebra is we're shouting a question up to Math God. Math God. And we say, Math God, where do they intersect? And Math God / algebra shouts back down and says, walls. That's the equation, that's the response that we got back from Math. So what would we interpret that to mean? We just asked, where do they intersect? And the answer is they don't. False means they don't. It means never. Which means what kind of system are we looking at? Parallel.
So how would the infinity
Thank you, Emily, for telling us to get started on this next problem. What do we do first? What do we do first?
start previous substitution.
There's my substitution sentence, and what am I going to do with it?
Your substitution sentence.
Very good. And then what do I write empty?
Oh, -6x plus 3 parentheses.
Perfect. Very nice. And then?
Plus the 2x plus 1.
Great. Very nice, Emily. So then we do our algebra, so everybody can follow along with your algebra. This algebra turns out a little different. What happens to variables? Negative 6x plus 6x? They still cancel. But now we're left with 3 equals 3, which if you finish moving all of your numbers to the right, we end up with 0 equals 0. Now that's a true sentence. 0 equals 0 is true. So once again, we shouted our question up to math God, and we said, where?
But now you're beginning to feel like that. But
Yeah. And then the answer that came back was true. So what does that mean about the lines? Where do they intersect? They always intersect. Exactly right. Now, I really like how those words work together. False means never, and true means always. And therefore, these lines are overlapping. Emily, does that answer your question? Yeah. Super good. So now going back to my original drawing, and you could do this on yours as well, there's something inherently false about parallel lines. The solution is false, whereas there's something inherently true about overlapping lines. The variables cancel out, and you're just left with a true sentence. The thing to keep in mind is, in parallel, variables cancel out, and in overlapping, variables cancel out. All right, well, dandy. So we've seen some examples of substitution, how we do it. We need a substitution sentence, which is y equals or x equals. We write the other equation empty, plug it in, solve for the first variable, plug it back into the original, solve for the second variable, check your work. Or if the variables cancel out, it's either parallel or overlapping. So there's one last thing to consider, and that is that you want to solve a system, but there is no substitution sentence yet. If they do not give you a substitution sentence, you must create it as an act of creation. Creativity. You get to create your own substitution sentence. And of course, I'm sure you'd like to do that as conveniently as possible without a lot of work. So let's look at that first one there, number 12. What would be the most convenient variable to solve for? X, Y, X, or Y? Which variable would be the most convenient to solve for?
The first.
Why the first one?
Because it doesn't have a number.
Right, both of those are kind of true. It's positive, that's true. But most importantly, there's no coefficient. So I just want to play devil's advocate here. Let's say I said, no, let's solve for that x right there. Well, watch what would happen if I did choose to solve for that x right there. Then I first have to move the 5y over, and that's fine. Everything's good. We have negative 4x equals 5y minus 10. But then all of a sudden I have to divide off the negative 4. Whether it's positive or negative doesn't matter. The point is I'm left with all sorts of fractions. And no one now wants to proceed to solve that, if you don't have to. Right? So it's no good to solve for a variable that has a coefficient because it leads to fractions. So choose a variable that doesn't have a coefficient. And then you don't have any fractions. Yeah.
over like to put the sign, like using the 5 and the 4. So the 4 becomes your numerator, becomes your denominator, right?
That's talking about perpendicular slopes. If you have one slope that's like +1 over +2, so up 1, right 2, up 1, right 2, the perpendicular slope would be those pluses. The perpendicular slope is you take the reciprocal and change the sign. So since this is positive over 2, negative 2 over 1, those two slopes are perpendicular, meaning that the two slopes would intersect at a right angle. Is that what you're thinking of? Okay, yeah. Okay, so let's solve for x, everybody. We're going to make this our substitution sentence. So first you got to take it, bring it down, write it down, and just go ahead and do the algebra. You add the 6y over to the other side. Whammo. We now have our substitution sentence. Now let me ask you a quick little question. Do you remember doing this in high school?
Yes.
Tiffany, do you?
Wow.
But do you remember? Not even remember how to do it, but just as a ringing bell. You're like, oh yeah, I guess I did that once. Or you're saying no?
It's been a while.
Okay. All right, that's fine. And then, Emily, did you say yeah? Valeria, do you recall? Not so much, Hector? You do, Nadine? Okay, I'm just curious. Okay, so at this point, we don't have to keep solving this problem, but if you'd like to, let's go ahead and do it. We have our substitution sentence. So what do we do with this one? Find it empty, right? So one of them becomes your substitution sentence, the other one becomes the empty one. And what variable are we going to write empty? Yeah, x, because we're saying now is equal to x. So I'm going to write -4 something minus 5y equals -10. So then we plug in the 6y plus 17. And away we go. So that's the act of substitution, plugging one equation into the other equation. The algebra is a little different, right? We distribute, and then we combine like terms, so -24y minus 5y is -29y. And then we'll have to add the 56 over. And so then we have -29y equals 46. I feel like something went terribly wrong. 4 times 17 is not 56. It's 68. Oh, ouch, I was so wrong. Not even a little wrong. I was so wrong. Sorry for leading me astray, folks. That was 68. Is that the only mistake I made? Oh, right, because 17 is 34, 68. Okay. So we add 68, and that makes 58, and now life is much better. Because 29 goes into 58. So -20, divide by -29, and we get y equals -2. Okay, well, good. I'm glad that we're solving one where we substituted for the x variable in order to solve for the y variable. So now, keep in mind your goal. Our goal is to find a coordinate. And so we need x and y. So far we've solved y, we still need to solve for x. How can we find x? Yeah, I mean, look at your substitution sentence. Your substitution sentence is already solved for x. So now it's just a matter of plugging that in to the original substitution sentence, writing that empty, plugging in the -2 we already found. And then we have x equals -12 plus 17, which is x equals 5. So now we have both parts and pieces, 5, -2. And at that point, we hope we're right. We don't know if we're right. We still have to plug that in. So I go back to my original two equations, and I'm just going to write in 5 there and there, and -2 there and there. And then we can do some mental arithmetic, or you can type it into your calculator. -6 times -2 is +12, 5 plus 12 is 17, that's correct. And then -20 plus 10 is -10, that's correct. Folks, I wanted to tell you one other thing that's really cool about this whole technique of using algebra. I told you before, this is if you're blind, right? You're a group of intelligent creatures on a planet in another part of the galaxy, but you don't have any eyeballs. So I don't know how you're still doing algebra. You just don't have graphing technology, right? So look at what we just found out. These two lines right here, what if I did graph them? They'd be somewhere, right? I mean, maybe one of them would be positive, maybe one of them is negative, I don't know. But the point is, even though I don't know what those lines look like, I know they intersect right there. Isn't that weird? I don't even know where the lines are. I mean, they could be like one there and one there, maybe there and there, maybe there and there. I don't know. And that's just so interesting. We would call this more like an existence demonstration. That we don't actually know anything about the nature of the lines. We don't know where they are. We don't know which direction they're pointing. We don't know their slope. We don't know their y-intercept. We're completely ignorant about these two lines. Yeah, there you go. But what I do know for sure is that they intersect right there. Isn't that weird? Normally, you'd think you'd have to know everything about the two lines first, and then you can say where they intersect. But algebraically, we know nothing about the lines, but we know they intersect right there. And that's weird. Isn't that mystical and wonderful how math can be so strange like that? Okay, let's go ahead and keep going. Number 13, which variable would you solve for? Yeah, that x right there, right? Because there's no coefficient. Okay, that's it for substitution, folks. How did you feel about substitution? Is it okay? You know, I don't know if it's like you're super excited about it, you want to write home about it, go home to your friends and family.
I have a question.
Yeah.
Is there, since you already found like the point in the graph?
Yeah.
Can you do like the slope formula somehow? Find like how the line goes?
Oh, like, yeah, how they go? Well, yeah, sure. I mean, that's an interesting question, Valeria. Like, let's say you were like, tell you what I'm going to do to graph these lines is first, I'm going to find their point of intersection. Oh, Valeria, this is a great question. You're batting 100 today. First, you got legs on animals, and now you're saying, I'm going to graph these lines by first finding where they intersect. And then going back over here, it just so happens that if you have ax plus by equals c, then the slope is equal to negative a over b. Okay? So now, if I do that here, the first line slope, so remember this is a, this is b, that's 1. Okay,